Hi there, welcome to this session on tokenization, the very first and arguably the most important step in how language models read and understand the text. What if I told you that language models don't read the words, they read tokens, and we are going to decode what it means. So we are also going to build a tokenizer from scratch, and we are going to use the techniques of byte pair encoding to build our tokenizer. So let's start with the very first step in how language models process text, the tokenizer. A tokenizer is like a translator. It takes your input, a sentence, a paragraph, or even a full document and breaks it down into a smaller chunks called tokens that the model can understand. Now, what are tokens exactly? Tokens can be whole words like hello or subword like hello or even single word like HELO, like depending upon how tokenizer is designed. This flexibility allows models to handle everything from common phrases to rare or even misspelled word. So before a model ever processes your input, the text goes through this transformation from raw text to list of tokens. So for example, the phrase hello word might be split into hello and world, and the token list is what the model sees, not the original sentence. So you can think of this like a stock symbols, right? Where instead of trading companies by their name, you are traded by the stock symbols. So are the codes. So the model process tokens the same way. So as identifiers, not as words. So now that we understand what a tokenizer does, so some of the key points to remember. Language models doesn't or don't actually understand text. They understand numbers. So when we say something like hello world, what model really sees is some numbers, some 1536 for hello and some 7896 for world. These numbers comes from predefined vocabulary where each token is assigned a unique ID. So as I told, for example, if I say, I love ChatGPT, then each one of the word is having a separate number being assigned. So the model never reads actual words. It always dealing with the numbers. It only sees and operates on these numerical token IDs. So this is a fundamental reason why tokenization matters. Because once a text becomes numbers, that's all the model learns from. So before we get into the more technical details of the tokenization, let's first understand why the tokenizations matters, right? So tokenization is just like some kind of a technical, formality. It is a fundamentally shapes how the model sees and understand the language. First, the foundation of understanding. Models don't read the raw text like we do. They only understand token IDs. So tokenization is what transforms human language into a machine readable form. Next is vocabulary constraints. A model can only process what exists in its vocabulary. If a word or a subword isn't in the vocabulary, it has to be broken down. Otherwise, the model has no way to understand it. Then there is the economic efficiency. So tokenization affects how many tokens your input consumes. Efficient tokenization allows longer prompts and lower cost. That is why if you see most LLMs API like GPT-4 have a strict token limit. Finally, there is a performance impact. So if we have a token, it splits, it lead to a better embeddings, which leads to better model outputs. So and also a subword tokenization also enables model to handle new or rare or slightly misspelled words more gracefully. So in short, tokenization is just the first step in your LLM. It is very critical step. Everything the model generates depend on how the input was broken down and broken down. Now let's talk about another important concept, how token IDs are actually assigned, right? That's the first thing. So first, these IDs are not random. They are not assigning something a random number. They are learned during a tokenizer training using a massive text data sets. So the idea is to assign smaller IDs to more frequent token. For example, the token the, one of the most common words, might be assigned ID 0, but something like this forms what we call as a frequency hierarchy. So common words get lower token IDs, rare or complex words get different token IDs, or maybe they can split into subwords, and those subwords may be getting a higher ID. So for example, let's take some complex word, for example, say quantization, right? So the quantization, the token arrays must split this word into quant and ization. Each of it has its own IDs. Something like quant might get an ID of 7698 and ization might get an ID of say 1728, something like that. Okay. So how does this happen? The tokenizer looks at massive text, identifies the most statistically useful chunks, and builds vocabulary around them. So it follows a statistical pattern, not just some a random number assignment. So that's why what we should remember is, to summarize, tokenizer is what which builds the model vocabulary. And what is vocabulary? That is the language the model learns. Now let's connect everything we have discussed so far and also discuss another important concept called model vocabulary. So basically, what is model vocabulary? The vocabulary is nothing but a complete set of tokens that model understands. It is created by the tokenizer during the training and then remains fixed for the life of the model. So every token that model might encounter, whether it is a common word like the or some subword like quant or ization, we discussed the previous slide, must be in this vocabulary. So you can see some examples in the table below, like different words are having different token IDs. So right, so these token IDs are just like a placeholders. The model uses them to look up, for example, something like a vector from its embedding table, basically a learned meaning for each token. Like we'll talk about embeddings in another session, but in this session we'll focus on tokenizations. So and then maybe like every model has got its own vocabulary size. If you take GPT-2, it is having 50,257 tokens, which is fixed for that model for rest of its life. So even if you want to fine tune that model, you have to get only the tokenizer for that model. So to summarize, the tokenizer builds the model vocabulary and then model learns to understand it. Now a question pops up, right? So what if I'm having only a fixed vocabulary size and then you give the model a word which is not there in the vocabulary, and so that it has never seen before? Does model fail? How does the model process? So if you say GPT is having only 50,257 words, what if I give some word which is not there in this 50,000 words? So that the answer is, it is not a problem at all, because of how subword tokenization works. So tokenizer doesn't require the entire word to be in the vocabulary. Instead, they're trying to break the words into something as known as subwords. So for example, take the word, for example, something like say conversationalist, right? It's a valid word, but assume this word is not there in your model vocabulary. But the tokenizer would still know how to handle it. Might split as a conversation or a list, or even more granular converse, something like ISIN, a list, like that, right? So as long as these parts are known to tokens, as long as it has seen the word con or it has seen the word a list, then it is able to break this word into multiple tokens, and then it knows that what is the the corresponding token ID for this. So that's what is important. So this approach gives a model like LLMs a major advantage. They can handle new or rare or compound words without failure. So what is important to remember is the tokenizer doesn't need to recognize whole word. Just meaningful parts of the word is good enough for the tokenizer. So now let's look at how this models we use like GPT or Llama actually build their tokenizers, because this steps comes before model training ever begins. First, they start by collecting massive text data sets from books, websites, code repos, everywhere in forums and more. So this makes sure that the tokenizer has seen a wide variety of a real world language. Now they train a tokenizer using an algorithm called byte pair encoding, or BPE for short. So these algorithms look at the data and learn which character pairs or subword appear more frequently. So from those patterns, the tokenizer builds a fixed size vocabulary, say maybe a 30,000 tokens or 50,000 tokens, which is compact but expressive enough to represent the language well. So finally, each token is assigned a unique ID, and that becomes the official tokenizer of the model, which will be used for all input processing during training and inference. So key point remember is the tokenizer is trained before the model, and it defines the vocabulary the model will learn from. That's what the important thing you should remember. Now let's discuss what are the different types of tokenization strategies used in language models. So first we have something called word level tokenization. This is where text split on white spaces. So a hello world, for example, becomes hello and world. It is very easy to understand, but it fails with a rare or misspelled words, because if a word isn't there in the vocabulary, the model can't use it. Then comes character level tokenization. This is best because it breaks every word into multiple characters. So hello becomes HELLO, like a split. This can handle everything, even brand new words or even typos. But the downside is the sequence becomes very long, which makes processing less efficient. So finally, we arrive at a sweet spot, which is the best of both worlds, which is a subword level tokenization used by algorithms like BPE. So for example, the word say unhappiness might be broken down into unhappiness. So these small chunks are statistically frequent. So the model can mix and match them to represent even new words. So a subword tokenization offers the best of both worlds: flexibility like characters and efficiency like words. That's why it is used in almost every modern LLM, including GPT, BERT, and Llama. So now that we understand how the subword tokenization works, so let's explore one of the most popular techniques used in today, which is byte pair encoding BPE. So we are going to discuss deep into this, and what the tokenizer we are going to develop is also based on BPE. So basically BPE it was actually also adopted in a lot of in NLP for a different purpose, to learn frequent and meaningful subword patterns. The idea is very simple. So BPE starts with individual characters and then merges the most frequent adjacent pairs to create a new reusable tokens, like as you see, like quantization, like that, right? So over time, this builds a vocabulary of a reusable chunks that help represent words efficiently, even if the word itself is rare, right? So how it works at high level: first, step number one, it splits each word into characters and add a end of the word marker like a maybe /w to preserve the word boundary. Yeah, as I said, if I say hello becomes HELLO and W. Then in step number two, it then counts all adjacent character pairs across your training test. If you say something like hello, it counts HL, then LL, LO, like that. It's keep on counting the adjacent pairs, and it's keep repeating this in a loop, like how many number of times you want to train, depending upon 50, 100, 500,000. It keeps repeating this in a recursive manner. Then it finds the most frequent pair and merges them into new token. For example, LL, it might become LL. So you repeat this process for a say fixed number of steps. Sometimes it could be 1,000, 10,000, 50,000, depending upon the amount of words or vocabulary you are training. So with BPE, we let frequency drive the vocabulary, and the result is a tokenizer that is fast, compact, and capable of handling rare words by breaking them down into familiar pieces. Next, take a simple example. We'll take some word called hello and then see how byte pair encoding builds a token for the word hello step by step. So we start by splitting the word into characters, including the end of words marker. Like so, as I told, we also discussed in previous slides, hello becomes HELLO and W. Now we run BPE merge step based on the frequency. Step 1, the most common adjacent pair is L comma L. So we merge into form LL. So now we have HELLO is our vocabulary, is our tokens. Next we merge E and LL. That becomes ELL. Now HELLO. Now we are having ELLO is the most frequent. So we merge it to get ELLO again. And then we are having HELLO. In step 4, finally HELLO gets merged into hello. Again, this depends on how many times I am doing this merge. For example, I decide to merge only 2 times. Then you will have the token as HELLO. So if you are having hello, another word which is not there in the model, it can still recognize because it has got H, it has got, maybe if you're having another word called A is also there, it is having L, it is having O. It can recognize these words. So now, but what should be important thing is that these merge step were not written, not like very static. They were learned automatically by the tokenizer from the large corpus based on what combination appears most often. So we are not doing a fixed rule here. We give the model a set of documents and we say go through each document this many number of times. Like in this example, we went through this word hello 4 times. Like that, I would say I have given you a big PDF file. Go through this PDF file for say 1000 times. Then every time it goes, it keeps on building that pair of words. It first picks up all the words and then it looks for adjacent words and then keep that in a recursive loop. I think you will understand more when I walk you through the code in the coming slide. When you walk through the code, we take a PDF file, we extract all the words from that PDF file, and then we take every word and try to tokenize it. You will better understand what exactly when I say BP, where it matching the pair and then doing a recursive loop. Okay, now let's start working on building our own tokenizer. Before that, let me show you the PDF file I'm going to use. I have this PDF file. Now we are going to build our tokenizer. That is, we are going to build our tokens based on this PDF file. Now let's head back to our Jupyter notebook. So this is Jupyter notebook. So first thing is that we need to install this package, SpyMe PDF, so that we'll be able to read the PDF file. Okay, so while this is installed, let me walk you through this code. In this code, what I'm trying to do is we are reading this file, we are passing the file name here, and then using this fits open, we are open the file, we are reading page by page. I'm loading each page and converting that page into text, and then removing any special characters, and then converting all the words into lowercase, and then we are building our corpus. So when you execute this, you will see that this is a top 10. I put only 10 words from this. It will have a lot of words, but it is having like 17,012 words, out of which I just printed this 12 words. So that means this entire PDF document is now converted into this particular words into this our corpus. These are our corpus. Now we have to start the pre-processing part. So of our corpus. So what we do in pre-processing. So this is a first step as we discussed previously in the BPE encoding, in the BP process. So we start by creating the default dict called word frequency here, and then what we also create another called vocab. Okay, and then what we are trying to do is we initialize this default dict vocab, and again the reason we are having this is this will store vocabulary in a more format suitable for BPE. So now what we do is for each word in our frequency dictionary, we convert the words into list of characters and then add W at end of each word. You can see that we're converting a list of words, we're getting a tuple out of this and then creating a W end of this. So by end of this function, if you run it, you will see something like this. That means every word, for example, information, we broke down into small in for like MATION and then we added W. This will tell me that how many occurrences of this information in this document, right? How many times this particular word came. So that word, and then every time I see the word, I'm splitting into characters and keeping a count of it, because we'll be using this later when I'm doing a byte pair encoding. So now that we have the initial vocabulary, the next step in our BPE process is to find how frequently each pair of adjacent tokens appear. That means if you are having something like S and Y, how frequently S and Y appear adjacent, like S and T, how frequently they appear. So that's what we are going to find with the get pair frequencies. In this method, we are interested only in how frequently they are happening. So we start again by creating a default dict. I have called a variable called pairs to hold our token pairs and their frequencies. Now for word token or frequency in vocab items, vocab item is what we got it initially here, right? Here, vocab is what we are having, all list of all these things are there in vocab items. Then we loop through each one of them, each word, and then what we should remember is when we loop through each word is stored as a tuple, right? With ending with W as its ending character. So for every word, we look at each pair of adjacent tokens. So if you see this word information, we'll see the adjacent tokens like IN, NF, FO, RM, AT, IO, ON. Like that, we look at the adjacent pairs, and then we then increment the count of each pair by the word's frequency. So how many times this? So once we have gone through all the words, we return dictionary pair of frequencies. Now maybe you'll understand better if I run this cell, you will see the output. Now you can see that this S and end of this one is appearing 2890 times. So basically this one we are only computing the get pair of frequencies because we'll be using this when you do the merging and training process. So for that reason, all I'm doing here is that we're not doing anything. We are just only counting frequencies, and then we are creating again a tuple where the each word, if I print this, it tells me, for example, T and I is coming 11518 times. That means T and their adjacent pairs, that many number of times this word pair is coming. Okay, this is called get. This is the get pair frequencies. So now we move on to the heart of the BPE algorithm. This is the one. So far we have broken down we loaded all the word PDF files into vocabulary words, and then we broken down each word into multiple characters. We counted the frequency of adjacent characters, right? Again, we build a characters, and then we counted the adjacent characters. Now we know the characters and we know how many times each adjacent character appear in the text one. Now our next process will be actually doing the merging process, right? That's where we are having this function merge pair. This will take the argument as the pairs to merge and the current vocabulary. That's what you could see, that when I'm calling merge pair, I'm actually passing this the pair and as well as the vocabulary. Now what it is doing is we start by initializing this default dict, okay, called a new vocab, okay, to store the updated token sequence after merging. Then for each word in the vocabulary, we walk through its token list, right? We look at every pair of adjacent tokens here. Okay, we see word token of I. Now I'm seeing whether this particular adjacent tokens in the word is actually available in the pair, right? If it is available in the pair, I'm going to add that. If you find a match, let's say this pair, say F and O, okay, we merge it simply by concatenating F and O and add it as a single token to our new word. This is where you're merging. Suppose we are merging, say for example IN, and then adding it as a single token like IN, F4, like that we are merging. So this is only merging only adjacent words. Now by end of this, I'll be getting a new vocabulary. If the current pair is not there, that means the word I'm trying to merge is not there, we just copy the current token as is. So after scanning through the whole word, we convert the new token list into tuple and update the new vocabulary with the same frequency as the original word. So now we'll run this and see this. Now we can see that vocabulary size after merge. So we'll try to print it. Now when you go to train part, we'll understand what exactly is happening, why I am doing this merge. Now that what we have done, again I'll summarize. In this last pair, we looked into each vocabulary. We compared that with the pair what we have defined the previous cell, and then we did the merge of the words if they appear adjacent token. Now the next cell, what we're trying to do is, now we need to put everything together. This is where we do the byte, this is where we are having this called train BPE function. This is where we are going to train our tokenizer, so which takes into our initial vocabulary. When I'm calling train BPE, you can see the vocab. Remember, vocab is what I actually created here, right? And then number of merges. Thus I can decide whether how many times. Let's do, for demo purpose, let's start at 50. Then I'll show you difference between 50, 100, 150 and 200. We can see how our vocabulary changes based on that. So I'll make a number of merges 50. Now what we'll do is, we initialize an empty list called BPE merges, okay, to keep track of sequence of merges. Then we'll go through let's walk through this loop one by one. So we are having this for loop where we compute the frequency of all token pairs in the current vocabulary. Get pair frequencies, right? So that's what we did here. Get pair frequency method we wrote. So we get the pair frequencies of all tokens in the current vocabulary. So if there are no more pairs left to merge, we'll simply come out of the for loop. If we have the pairs to merge, what we'll do is, otherwise we find the most frequent pair and we'll just log it to console so we can monitor the training process. So we check the most frequent pair and then log it into the monitor. And then we'll invoke this merge pair method. We remember merge pair method we wrote here, right? Where it takes two adjacent words and checks whether this word is there in the pair. If it is there, it will add it to the new vocabulary. Then it add it to the BPE merge append. Pair gives vocabulary. Then it appends this to the new BPE merge. And also we store the merged pair in the BPE list. We will use again this for the later use. What are the vocabulary we are getting? We are also adding this pair to the BPE merge so that we can use it for the later purpose, right? And then once this loop completes, either because we have reached the merge limit or we ran out of pairs, any one of them, we return the final vocabulary and full list of merges performed. So let me run this. That's where you can see now we are running trainings. You can see that I did 50 times I had done this, right? It's very less number of times. Now we can see that every time I do the merge, it is trying to find, it is only logging the merge with the highest frequency. That's what I'm having, max frequency. So in this number, merge number 1, this S and end of character appear 2890 times. It's the maximum number of times. When you did second time, you need to run the merge again. Because it's a kind of recursive, right? It does, yes, it'll again, when you go to next time, for example, if first time when you did the merge, you might have, for example, take this word. First time if you did a merge, I and N could be there, in could be there, okay? Now when you did second time merge, your token will not have I and N but in. You will have in in for RM at IO like that. Now when you do second time merge, now in will be merged with in F like that, right? It keeps on merging. That's why more number of times you do the merge, that many number of you will have a different output altogether. So now I know we'll come back to this method again by increasing the number of merges. But let's see the 50 merges. If now if I give this, if I want to find a new token, okay, how how it is going to convert this, right? Because we have now trained the model. Now we are going to give it language amazing transformer. I want to show you if I run with 50 times merge how the output is going to be, if I run 100 times how the output is going to be, with 500 times how the output is going to be, right? But quickly look at this method. We are calling this apply BPE method. So I'm having this test words, I'm looping through. For each word I'm calling BPE. So what I'm doing is I'm passing this word and this BPE merges. The BPE merges is what we have trained on. This is our BPE merges where we did the training process. Now what we do is then in this method we start by breaking the word into individual character. So now if you put language, it again does same thing. It breaks into individual character, just like a training, and then we add a W end of the character. Now then we loop through each merge in the same order we learn them. So for each merge pair we scan through the current list of tokens, okay, because this current list of tokens is what what we have here, what we got. So as long as this is less of this one, if this length of token minus and this one, that means the token, like now we are checking with L and A if is available in this merge pair, right? For example, if you find L and say where L and A is there, so we concatenate these two tokens, say LA, if that is available, then we add that to our new list. So if there is no match, we just put them as it is. For example, in our vocabulary, if L and A is there, I just put them as, merge them and put it here. And then if I don't have, I will add it. Now this becomes new. Now I keep on repeating this. Now I repeat this for L, A. Now I'll repeat it for N and G. Then I'll repeat for U and A. Then I repeat for G and E, right? So I keep on repeating this till I run through all the, till I process this entire word. At the end, we return the final list of tokens. Now let's see what happens. Now if I see here, right, when I pass language, it has printed only L, A, N, okay, A, G, U, A, G, because I just ran only 50 times. My initial BPE merge only 50 times I performed. Now let's see, we will perform the same BPE merge 100 times, okay? And remember now, for language, you are seeing L, A, N, G, U, A, G. And then when I perform 100 times, let's see how the output is going to be when I do the BPE merge 100 times. Now let's run this cell. Now you can see that you are having, the transformer. For example, it was a TRAN. Now it is having transformer, right? Because I did more merges now compared to the previous time. Now let me see one more. Let me increase it. We do this 500 times instead of 100 times. Now it might take a few seconds to do this 500 times merge. And now let's run this our cell. Now you can see the language is not broken. It has converted language into language only. Amazing transformer, right? You can see that depending upon the number of times I'm merging, your the way it is tokenizing is changing. Now to complete our now do the detokenize. That means we have tokens, we need to convert these tokens back into detokenize. So that's where we're running this detokenize function that takes a BP token as input. If I'm passing detokenize token BP as input, so we simply join all tokens into a single string, and then we remove that end of this end of W character what we added earlier, and then replace with the string. So now we can see that when I run, it is actually doing a detokenize. So we'll come back to this method later also again, but most importantly, let's now go and see the create the token vocabulary. Now we did all the merging, we ran 50 times. Now we are having the BP merge, everything's done. But we have, after we complete the training and finalize our vocabulary, let's create a proper token vocabulary, just like how modern tokenizer do it before feeding tokens into the model. This is where we are having this create token vocab method. Yes, first we initialize set to collect all the unique tokens and a default dict to count how often each token appears across the entire vocabulary, right? Then we loop through all these word tokens in the final vocabulary what we are having, and for each token in each word, right? This is the, okay, let me also show you this final vocabulary. First, before that, let's walk through. Yeah, now what we do is we actually loop through each tokenized word in the final vocabulary, and for each token in each word we add it to the set of all tokens and update the frequency based on how often the full word occurs. So once we have all the tokens and their frequency, we sort them by frequency so that we know which is the most frequently used token, which is the less frequently used token. Next, we create two mappings, token to ID and ID to token. So token to ID, which is mapping each token to unique ID, and then an ID token is a reverse of it. We then return these mappings along with the frequency dictionary. So what happens by end of the, if you run this one, now we are having ID 0 for the 1 is off, like that we created different IDs. So we are having total unique tokens of 520, and then for each token we have given this. Again, this also depends upon how many times I'm running my merge. If I'm running 52, it might be a different number of tokens. So far we have created this method. Now in the last step of our tokenizer pipeline, we have to map this BP token to their corresponding IDs. Just like what happens when before feeding, suppose if you are something like if you are building a neural networks and how you feed it, we actually need to map this BP token to the corresponding IDs. So that is where we are having this function tokenize to IDs. It takes a word and then the BP merger what we have in the previous method we learned during the training, and then token ID mapping. So first we apply the BP algorithm to the word, apply BP function we defined earlier, which gives us a list of string tokens. Then we loop through each of these tokens to the word using apply BP function. Then we loop through each of these tokens and then convert it into numerical ID using the token to ID dictionary. So we build the token to ID dictionary here. By using the token to ID dictionary, we convert, we basically looping through each of these tokens and convert using the token dictionary. Here, one thing to remember is if you see the code, if we ever come across a token that doesn't exist in the dictionary, that's what we saw in Amazing, which was not in dictionary, which is rare if the training was thorough, but we log the warning, that, something like we log a warning that this token doesn't exist. So otherwise, otherwise we default that to -1, that, to indicate it is unknown. Finally, we return both the string tokens and their corresponding token IDs. So let's do this testing now. I have written a simple test function here. So now we can test this one. Now we can see this language, token ID is language. This is the token, language is the ID. So Amazing, you will have A, M, A, Z, I, N, G. This is the IDs for each one of these tokens. Transformer, you are having transform, and this is one of these is a IDs for each one of them. In the next in the last, we again do the same process of detokenizing, okay, where we again we deconstruct detokenize using only the token id. That means if I give a token id, I just like a model might generate during inference and then reconstruct the original word. So this is where the function detokenize. Let's run it out. I think it's very simple. Now we know that this id 157 correspond to language, then 1982 correspond to amazing. Now in the finally, once we are done with everything, we should be able to save whatever we have done our work for the future use. So now, because we built and tested our byte pair encoding tokenizer, and we should be able to save it just like it would be with a real model tokenizer, right? That's where this function save tokenizer takes three components: token id, the mappings, the reverse token id, the mapping, and then the BPE merges, and then just simple file name. So I'm storing everything in a .txt file. Now inside the file, we first write merges section where each line lists token pair that was merged in the exact order we learned them, because the sequence is very crucial when reapplying BP to the new word. Then we write vocab section where each line contains a token and its corresponding ID. We make sure that to write it using a ID to token mapping so that the order is preserved. Next, the companion, this function load tokenizer lets us read the file back in. It parses a file line by line, switching between merges and vocab mode depending upon the what section we are in. Right, now let's run this. So now the tokenizer is saved. Let's see where this file has been loaded. bp tokenizer.txt. Now you can see that this is our tokenizer. Now you can see that there's a section called merges where we are having merges, and there will be a section called vocab. Scroll down. Yeah, this is a section called vocab. You can see that you are having the word and then its corresponding token IDs. So this is how you build a tokenizer, and then you can keep using this tokenizer in your model.